Hi students, how are you? I am Dr. Suresh, Assistant Professor in Physics. Welcome to my channel. Today we will discuss orientational or dipolar polarization. This is third type of polarization. We already discussed about electronic polarization, ionic polarization in previous classes. In this class, we will in detail discuss about orientational polarization or dipolar polarization. Have you ever wondered why water has dielectric constant is very high, that is 80, compared to solids? Some solids are having single digit numbers, so A7, 8, 10, like that only the dielectric constant is there. But water having 80, dielectric constant is 80. This is because of this orientation polarization only. Water is a polar molecule. Due to this polar molecule, water having high dielectric constant considered to the solids. Some molecules have permanent dipole moments even without any applied field. These are called as polar molecules. Examples: water, H2O, HCl, NH3, CO, CH3, Cl, etc. These are some polar molecules. For example, consider water, that is H2O. Molecular structure of water is like this: O2 minus, this is H plus Cl. The dipole moment is from negative to positive direction, it is in this direction. This is the resultant dipole moment. This is mu r, it is nearly 1.85 d. Here every molecule having permanent dipole moment without any electric field. If you didn't apply any electric field also, these molecules are having some dipole moment. These molecules are called as polar molecules. Here the dipole moment of all these molecules without applying any electric field they are in random direction, not in one direction. They are aligned in random direction. This is due to temperature is the reason for this randomization of the dipole moment. Okay, if you apply electric field, that implies if we apply an electric field E, these molecules, dipole molecules, will align in one particular direction. Here the dipole moment is not equal to 0. We will see some dipole moment will occurs in these molecules. In this case, the dipole moment, the resultant dipole moment is 0. The polarization, orientation polarization also 0. Here the dipole moment not equal to 0, and it is some orientation polarization will occurs in this case if you apply any electric field. Here we should know the competition between temperature and electric field. Here electric field tries to align dipoles in particular direction. Temperature tries to randomization of dipoles. This is exactly like the compass needle example. Many small compass needles placed on a table. There are scattered randomly on table. Bring a magnet near to the table. What happens now? These needles will align in particular direction because of this magnetic field. If you shake the table, what happens? If you rigorously shake the table, here then these dipoles, these needles will align in different directions due to this shaking. Here the shaking is temperature, the magnetic is electric field. This is the perfect example for this temperature and electric field competition in orientational polarization. Here the scientist Langevin analyzed this competition between temperature and electric field. He given a mathematical relation between this temperature and electric field, that is the polarizability, orientational polarizability is equal to mu naught square divided by 3 kBt. Here alpha naught is orientational polarization, mu naught is dipole moment, Kb is Boltzmann constant, that is 1.323 into 10 power minus 23 joule per Kelvin. T is temperature in Kelvin or absolute temperature. Here we should know the temperature dependence. Orientational polarization decreases if you increase the temperature. That means at low temperature What happens at low temperature means less thermal randomization, more alignment. That means large PO, polarization PO is very large at low temperature. At high temperature, what happens at high temperature? More thermal randomization and alignment of dipoles will happen. So here clear understanding that if you increase the temperature of water, the molecules will get randomization and the polarization, orientation of polarization is decreases. In the formula also we know the alpha naught equal to mu square by 3 kBt. Alpha naught is indirectly proportional to temperature. If you increase the temperature, orientation of polarization decreases. Summary of this class. It occurs only in polar molecules. It is strongest dependent on temperature. Response time is low, that is 10 power minus 10 to 10 power minus 6 second. It works at to 10 power 10 Hz. That means it will work at low temperature to 10 power 10 Hz. Microwave frequencies, radio and microwave frequencies. Above 10 power 10 Hz, orientation polarization will become zero. In non-polar materials like silicon, germanium, the orientational polarization is zero because there are no permanent dipoles in these non-polar materials like silicon and germanium. Here another polarization is space charge polarization, that is denoted by PS. Here what is space charge polarization means? Generally materials are having some defects, but in defects also charge carriers are there. If we apply electric field to the materials, the charge carriers present in defects also polarizes, and this type of polarization is called space charge polarization. But comparing to electronic polarization, ionic polarization, orientation polarization,